Chapter 5, Thermochemistry. I hope you guys have your notebook, calculator, pencil ready. Might be a good idea to have your book opened on your tablet or on your computer, on your iPad. If you've got your book, you'll notice the picture at the beginning of the book is a picture of donuts. And I always start chapter 5 by showing you guys that picture, and occasionally I have been known to bring donuts for the class. So enjoy a donut and think about thermochemistry. But this is a neat story, guys. All of us at some point have looked at the nutrition information on food. Looked at the calories, looked at the fat, the sugar, whatever. But the story that starts chapter 5 in your book, this was in 1997. There was a diet company that was selling donuts, and they were marketing these donuts as low-fat, carob-coated donuts. Carob is a low-fat chocolate. Anyway, the label said that every donut had 3 grams of fat and 135 calories. After consumers complained, it was found that the FDA did some tests, found the donuts actually had 18 grams of fat, not 3, and that there were 530 calories in a donut, not 135. And that investigation led to criminal indictments on, I don't know, the people, the CEOs, I don't know who it was. But part of thermochemistry, if we were in class, we would actually do a lab. You guys would sometimes we burn peanuts. We've been known to burn marshmallows, Frito chips, but we burn them and we measure how much water burning them melts, and we can calculate that back to how many calories are in the food. And perhaps you'll get to see that done as one of the labs instead of doing it yourself. But let's talk about energy, because that's what thermochemistry is. It's talking about energy in a reaction. Potential energy. Y'all know what that is. I mean, if we were in class, I would pause and say, what is potential energy? What is kinetic energy? And y'all know kinetic energy is motion. Molecules have motion. Potential energy is stored energy. And when you're introduced to these concepts in physics, kinetic energy, we do balls rolling down a hill. Like at the top of the hill, the ball has a lot of potential energy. When it starts to roll down the hill, the potential is converted to kinetic, etc. And we talk about these transfers. So in physics, we talk about big scale things. But in chemistry, we're talking about chemicals. So we're going to get on a molecular or an atomic level. And molecules are moving. They have kinetic energy. Think about the movement of molecules in a solid versus a liquid versus a gas. Gas molecules are moving more, so they have potentially more movement energy, but you also know gas molecules are more dispersed and not as densely packed as in a solid. Molecules also have potential energy within the bonds. It takes energy to break a bond, and when that happens, sometimes compounds release energy, sometimes they absorb. In understanding the thermochemistry chapter, we're going to talk about some terms, first off, that we have to understand. We have to be sure we know the difference between the system and the surroundings. Okay? The system is defined as the part of the universe that is of interest to us. The surroundings is everything else. Okay? It's very important that you get your head wrapped around these two definitions and you understand them. Not memorize what it says, but can apply what it says. Y'all, a couple of weeks ago in lab, you had a beaker And you had a blue solution in that beaker. And if you'll recall, that's because it was blue because it was a copper solution. And you guys weighed out some zinc, little granules of gray zinc, and you put it in that beaker. And what happened is it started to fizz, and the blue color of the solution that was there faded. Do you recall that? And the zinc that you put in the beaker actually dissolved, and what ended up in the beaker was reddish brown copper. Okay? But when that process was happening, I went around the lab and I told y'all, touch the beaker while it happens. And you guys felt that the beaker was hotter. It got hot. It warmed up. Okay? In that example, the system, the part of the universe that was really of interest to you, the system was the copper and the zinc, okay? And in that reaction, the copper started out as copper-2 ions, and the zinc was solid zinc. That was the system. So what was the surroundings? Yeah, everything else, detail it. What is everything else, okay? It was an aqueous solution. So that meant the surroundings included the water that it was in. The surroundings included the beaker that it was in, the air, the lab bench, you. Okay? All of that was the surroundings. The system for us in chemistry, guys, the system is going to be the chemicals involved in the reaction. The surroundings is going to be everything else. In thermochemistry, oftentimes the measurements you make, the measurements are many times on the surroundings, but you can calculate those measurements to get back to what's going on in the system. Okay? Thermochemistry is the study of heat, transfer of energy in a chemical reaction, okay? So, thermochemistry is the study of heat transfer in a chemical reaction. And at some point in your science career, in your science classes, y'all have heard of the law of conservation of energy. Now, this is not to be confused with way back in chapter 2, we did the law of conservation of mass. Remember what that said? That matter is not created nor destroyed in a chemical reaction, that the mass is not created nor destroyed. Okay, this is different. This is the law of conservation of energy. Don't confuse the two. Law of conservation of energy says that energy is neither created nor destroyed. This law is central to this chapter. Understanding system and surroundings is central, and understanding the law of conservation of energy is central. You are using that law when we go back to that scenario of the ball sitting on the top of the hill. At the top of the hill, it has potential energy. When it starts to roll down the hill, the potential is converted into kinetic. When it reaches the bottom of the hill, that kinetic energy is dispersed into another form. All those statements are statements around the law of conservation of energy. That energy is not being created nor destroyed. Okay? We have these terms that we use when we're talking about the transfer of heat energy. Okay? And realize heat is thermal energy. And it's a good place to point out that sometimes we use the word heat in our everyday life, incorrectly. When you're cold in a room, you might say, hey, could you turn up the heat? Or if it's hot in a room, you might say, could you turn down the heat or what have you? But guys, when you go to the thermostat in your apartment or in your home, the number reading on the thermostat is a temperature. The temperature is not the heat. Okay, that's just how we always say it, but they're different. So when we're talking in thermochemistry about heat, we'll talk more about that and introduce it more in a little bit. Realize that heat and temperature aren't the same thing, okay? But heat is thermal energy. Just a second ago, when we talked about this copper and zinc, I told you guys that when you touched that beaker, you know, it felt warm to you. The temperature of that beaker increased. Why did the temperature of that beaker increase when the copper and the zinc were combined together? It's because the copper and the zinc were releasing the heat. And releasing heat is going to make the temperature of something go up. We use terms to define this in chemistry, and these are terms that I think you've probably heard of: exothermic and endothermic. An exothermic process is a process that releases heat, like that copper and zinc process. If a process is releasing heat, how is that going to feel to you? It feels hot to you. Endothermic process, we're kind of using the law of conservation of energy a little bit here. That process absorbs heat. Now, how would that feel to you? If a process is absorbing heat, it feels cold to you. And let's focus on that. How can something that absorbs heat feel cold? Some people, that might make perfect sense, but some people start thinking about that and think, hang on a second, if you're absorbing heat, it ought to warm up. It goes back to the system and the surroundings. What are you? You are the surroundings. If the chemical process is absorbing heat and you're the surroundings, then it's absorbing it from you. It's going to feel cold to you because you are transferring your heat to the process. A good example is ice melting. That could be written like this: H2O solid yields H2O liquid. That's ice melting. How does that feel in your hand? It feels cold. Why? Because the H2O is the system. It's absorbing the heat from your hand. If we had to look at this process in reverse, and instead of ice melting, what if we talked about H2O liquid to H2O solid? Water freezing. Now, that doesn't really feel hot to you because it takes some time for that process to happen. But does it make sense to y'all that in order for water to freeze, it must release heat to become a solid? Anything has to do that. To go from a liquid to a solid, it's the substance has to get rid of the heat to go to the solid phase. Likewise, to go from a solid to a liquid, any substance has got to absorb heat to melt. It's also water or whatever you're talking about, it's got to absorb heat to evaporate. So even if you were talking about water going on to evaporate, or any substance as it goes from a solid to a liquid to a gas, heat has to be absorbed for that process. Your book has a picture, and if we were in class, I would show this picture and we would discuss it and see what I hope you guys knew about it. And you can see I captured a little bit of the title at the bottom, the Hindenburg. Hindenburg was a German airship. The Hindenburg was filled with hydrogen gas. Hydrogen gas is lighter than air, so that's why the ship floated. This disaster was caused because, well, there's one theory actually. This is one theory. That the hydrogen gas, which is flammable, guys, y'all have produced hydrogen gas in lab in a couple of your reactions, and you had to do it under the fume hood. But the hydrogen gas we're talking about in this picture is filling that balloon. So it's much more hydrogen gas than what y'all made in lab. Well, you guys know that air is about 20% oxygen, okay? What happens potentially when hydrogen and oxygen combine? Well, they combine to make water, okay? Usually they make water vapor because this process is exothermic. What does that mean? It produces heat, okay? So it's generating heat when that reaction happens, and it's really just a bad combination because the process is producing heat. You've got hydrogen gas around, which is flammable. You've got oxygen, which you know a fire needs in order to burn, and that can be catastrophic when you have all these perfect conditions, and that catastrophe could be, it is one possible reason for why this Hindenburg airship exploded. There's another theory that it was because of the paint, that the paint that the ship was painted with had lead in it, and the frame of the ship, that those metals reacted in what's called a thermite reaction. But there's different theories as to what happened here. There's another event in the history of our nation that we know this process. This is the reason this tragedy occurred. Now I want you to pause a minute and think about what that other tragic event would be. Because if we were in class, I would pause and I would be letting you guys think and I would be taking your answers. So pause for a second. And what do you think the other event was? Tragic event in the history of our nation. And that reaction is the reason. A lot of people will say a bomb. That's usually what I get, like a hydrogen bomb. That's a popular answer. That's not it. The event was a space shuttle explosion. A lot of times people will guess that. Which one? The Challenger explosion. So read about that. That reaction is the reason that the Challenger exploded and all 7 people on board were killed. Okay, so we've talked about system and surroundings, exothermic, endothermic, define thermochemistry. Let's mention now some units of energy. As we mentioned when we started talking about the donuts, calories is a unit of energy. I want to point out that there's a difference between these two words I just wrote, and the difference, it's subtle, but it's in the capital letter. The capital C calories, that's used for food calories, okay? The lowercase c calories, those are typically the calories that we are calculating in chemistry. So many times the calories we calculate are lowercase c. Guys, that's not going to be a test question. But I just want you to be aware that there is a difference in the calories on a nutrition label. Another unit of energy, and this is a very common one that we will be using, joules. And the way these two numbers are related, a calorie is equal to 4.184 joules. You do not have to memorize that conversion. If I ever wanted you to recall that, I would tell you, I would remind you of that conversion. But the joules are the unit of energy that we will be dealing with most often. The way you abbreviate these units, you know how kilograms, y'all know to put kg, or meters, you know to use M. The way we abbreviate calories is CAL, and joules is abbreviated with a capital J, sorry. Now, We mentioned system and surroundings earlier. Let's go over, there's different types of systems. You'll encounter questions about this when you are doing the Learn Smart on Connect. There's an open system, a closed system, and an isolated system. Now, let me give you an example and ask you a question, and in doing so, you're going to define these systems. An open system, if you had a cup of coffee and you put your hand over that cup of coffee, what would you feel on your hand? Y'all know you would feel warmth. You would also feel steam. Your hand would feel moist. That is because an open system exchanges matter and energy with the surroundings. And so that open cup of coffee, the matter is the steam you feel, and the energy is the heat you feel. So open system would exchange matter, and energy with the surroundings. So a closed system, if we put that coffee in a thermos and screw the lid on, now when you touch that cup of coffee in the thermos, now what do you feel? You can feel that the thermos is warm, but you don't feel the steam anymore. So how would you define a closed system? It exchanges energy with the surroundings. And I keep asking, what would you feel? Why? Because what are you? You are the surroundings. Now, an isolated system, it's no exchange with the surroundings, okay? So that's a rare specialized case that's only going to happen in a lab environment, okay, to have an isolated system. So we're going to put that cup of coffee in an insulated container, and it's going to be a vacuum that's not going to allow the pressure to change. There's going to be no pressure. That's just a rare system. Okay? In dealing with thermochemistry, we often define the state of a system, which is explaining values like it's the energy of the system, its temperature, its pressure, etc. In defining the state of a system, we label things as a state function. And I'm going to give you the definition, and then I will give you an example of what that means. A state function, its properties that are determined based on the difference between the initial and final states of a system regardless of how that difference is achieved. Okay? For example, your book uses this. Guys, let's say we're in a building that has 10 floors. If you start out on the first floor and you end up on the 4th floor, start 1st floor, end 4th floor. What's your change in floors? Your change in floors is 3 floors. Because to measure a change in something, change in anything, it's always the final minus the initial And in math, have you ever seen the triangle in front of something? You might say delta. Delta means the change in. You take the final minus initial. So your change in floors is 3 floors. Now, that's a property that's determined based on the difference between the initial and the final states of the system. It didn't matter how you got from the first floor to the 4th floor. I mean, the two most popular choices would be to either take the stairs or take the elevator. It doesn't matter how you do it. You are going to change 3 floors. Now, we all know you might have got on the elevator at the 1st floor, forgot to punch the number, and you ended up on the 6th floor, but then you had to punch the number and get off on the 4th, right? Your change in floors was still 3 because you started at 1 and you ended at 4. It didn't matter what happened in between there. Okay? A least popular choice would be to maybe rappel up the outside of the building to go from the 1st floor to the 4th floor. So the change in floors is a state function. It doesn't matter how the difference was achieved. What about this? How much work did you do to go from the 1st floor to the 4th floor? Guys, if you took the stairs, that was going to take some work on your part. That would have taken more work than had you ridden the elevator from the 1st floor to the 4th floor. So see, the work that you had to do, work is not a state function because the work you do is going to depend on the path. It's going to matter how the change happened. Also, the time it took for this to happen, that's going to depend on the path because if the elevator ride went straight from 1 to 4, that would probably take less time than taking the stairs from 1 to 4. So time is not a state function because it matters how the difference was achieved. So some examples of things that are state functions are volume. Y'all know V is a symbol for volume. That's a state function. Temperature is a state function. Internal energy, that's what U is. Internal energy. Those are state functions. Okay, a few of the examples that I just gave you that are not state functions. The time is not a state function. T is time. The work you do, the symbol for work is W. That's not a state function. There is an easy way to tell the difference between variables that are state functions here and those that are not. This is not foolproof, but y'all usually, if the symbol is given a capital letter, it's a state function, okay? Notice, I'm not talking about the units. I'm talking about the variable because like volume is measured in milliliters, okay? The M's lowercase. So it's not the units that tell you the state function, it's the variable used to define that. There's a couple of little exceptions on that, but if you're unsure on how to apply the definition, if you'll look at what stuff has a capital letter, then that's probably a state function. From this, we are ready to move on to the first law of thermodynamics. It's based on the law of conservation of energy. So the first law of thermodynamics says that energy is neither created nor destroyed. But is transferred or converted from one form to another. So how we can measure changes in energy is we can simply measure the change in internal energy of something. That is the difference between the final and the initial states. Remember the delta triangle? It's always final minus initial. Don't let that mess you up later, because I'm telling you now, it's always final minus initial. And internal energy has two components of kinetic energy and potential energy that's determined by a lot of factors, y'all. The motions of molecules, masses, the electrons, etc. And it's impossible to measure all of this accurately. So we can measure the difference between the final and the initial states. Another way to think of this and measure and change of internal energy, final minus initial, and we will do this some, it's also sometimes the products, the internal energy of the products minus the internal energy of the reactants, because final minus initial, isn't that the final is the products and the reactants are the initial? So we can do final minus initial. Which brings us to our first formula. Delta U is equal to Q plus W. Where delta U means the change in internal energy. Q is heat and W is work. Each of these, the units of the internal energy and the heat and the work, the units are going to be joules, some form of joules. Sometimes you might see, instead of joules, you might see kilojoules. You know, if there's a lot of something, we do kilograms. And the relationship between these is just like you would expect, that there's 1,000 joules in a kilojoule. Okay? But what's important to note when using this formula is that we have to apply signs of positive or negative to the heat and the work. And how this is going to work, the system is what is of interest to us. Anytime heat goes into the system or work goes into the system, that's positive. Okay, heat or work going into the system gives it a positive number because the system's what we're interested in. Y'all, if it's going into the system, then that means where's it coming from? Has to be coming from the surroundings. Okay? But now if the system releases heat or the system does work, then the sign is going to be negative. And that might seem a little bit overwhelming at first, but there is a table in your book, table 5.1 in your book. It's on page 194 here in my book. It summarizes what I just said. Okay? Heat going into the system. Anytime something's going into the system, that's positive. Work done on the system, positive, because that's what we're interested in. Realizing that if it's going into the system, then the surroundings is losing it. Okay? And so now let me write a problem. Okay, so you might want to pause it to write this problem, write this question. Okay? So let's calculate the overall change in internal energy for a system that releases 43 joules in heat and does 64 joules of work. So, what are we calculating? The overall change in internal energy. We have to calculate the delta U. What is Q? Q is heat. And it says Q is 43 joules. What is W? W is work. And it says 64 joules. But then we have to read those numbers in context. It says a system releases this much heat. If it's releasing heat, that tells us the sign of Q is negative. It also says, and does this much work. If the system is doing the work, The sign of W is also negative. So, to calculate this, delta U is equal to Q, negative 43 joules, plus W, negative 64 joules. So the overall change in internal energy of the system is negative 107 joules. And that is the answer to that question. Let me ask you a second part to that. What is the change in internal energy of the surroundings? Well, this calculation says the system releases 107 joules. That means the surroundings must be absorbing 107 joules. So what is the change in internal energy of the surroundings? Positive 107 joules. Continuing on with that, same thought process on this question. What would be the change in the internal energy of the universe? Well, what makes up the universe? The system and the surroundings. If the system releases 107 joules and the surroundings absorbs 107 joules, then what is the change in the internal energy of the universe? It's always zero. That's the first law of thermodynamics. You can certainly expect to see questions about this on Connect, these kind of calculations. There's questions like that to practice in your book on pages 190. Even though that's only about a 37-minute lecture. Looked like it stopped recording and I'm not sure where it stopped. That would have taken a lot longer to lecture in class because we would have had discussion. Y'all would have had questions. I would have been pausing. Guys, give me your questions about it. If there's stuff I need to clarify, I'll do more videos. I'll explain what I can via email. But ask questions. We can learn from each other's questions.